right, ladies and gentlemen, today we're looking at chapter 35, electric circuits. Basically, the big idea here is that any path along which electrons can flow is what we call a circuit. And so the big thing about circuits is that most of us don't have much experience with them. We're too afraid to take them apart because they're expensive. And so over here on the right-hand side, we've got an electronic circuit board. It's probably for a computer, but I'm not 100% sure of that. We usually can deal with mechanical things pretty easily because we've, built Lego castles and we've played with mechanical toys and things like that. But we don't have a whole lot of experience with electric circuits, again, because of that expense thing. And if we take it apart, take our VCR apart, take our radio apart, putting it back correctly or incorrectly may not happen, and you may end up ruining it. So a lot of people just don't mess around with it. So what we're going to look at for electric circuits, trying to break it down into the easiest thing we can think about when we think about a circuit, is a battery and a bulb. And essentially that computer board we just looked at there runs on the exact same principles as a battery and a bulb. And as long as all of those same principles are met, it's going to work. But screw one thing up one place and it may screw up, a whole rest of the board because it doesn't have the right connections. So that's where electrical engineers and things like that come in, and they, make sure that things like that do work. But with a battery and a bulb, basically we've talking about a flashlight here. We have a switch. We turn it on. This completes an electric circuit. Once that circuit is completed or closed, the mobile conduction electrons that are in the wiring all just start to move. And once they begin to move, they can start to pass through the filament of the bulb in the flashlight and cause the bulb to go on, and then they drift from one side of the battery to the other side of the battery, and we have light. And so this is your basic flashlight. Again, has a case. This switch here is typically, I wish this was kind of cut away. There's usually like a little copper plate right here, runs from the top down here to the bottom. This battery here, when put in, would connect to the bottom plate. This battery here would connect or be ready to connect up here at the top to this filament or this bulb, which is inside of this little case. And essentially you complete a circuit here. If you push this switch forward, it connects all of the copper inside, and your light turns on. But there's several ways to connect a battery and a bulb from a flashlight so that the bulb lights up. But there's many other ways that you connect them and it doesn't work. The most important thing that we have to have is we've got to have this complete circuit, this idea that it has one continuous loop. And so we'd have this bulb filament. We've got to have some kind of wiring that runs from the positive terminal at the top of the battery back down to the negative terminal at the bottom of the battery and ultimately touches to the bulb in some way. And so one thing that's very important to realize is that electrons flow beginning from the negative part of the battery. Okay, so they leave the negative part of the battery, they then go into the wire. Then the wire goes to the side or the bottom of the bulb, depending on how the bulb is set up. The electrons then pass from the side or bottom of the bulb up into the filament, and then they go back. Those electrons go back out the bottom or the side, and then back through the wire to the positive part of the battery. We have that complete connection. The electrons are flowing through the filament, and so the bulb lights up. Once the electrons pass back through the battery, they are then completing the whole circuit and essentially do the loop again. And so here in A, there's many ways to set up a bulb and a battery that's not going to work. Most of them involve not having a positive and a negative both being touched along with your battery. And so here, positive, negative, go into the battery, no problem. Positive, negative, going to the bulb, no problem. Positive, negative, going to the bulb, no problem. But these guys all lack that either positive or negative connection or a connection to the bulb. So flow of charge in a circuit, again, is very much like the flow of water in a closed system of pipes. We talked about this in chapter 34. It's a good analogy. It's not perfect, but it definitely works to a certain extent. And so in a flashlight, battery's analogous to the pump that would push the water around. The wires are analogous to the pipes. The bulb is analogous to any device that operates when the water is flowing, maybe a fountain or something like that, a sprinkler, whatever it happened to be. But when a valve in a line is open and the pump is operating, water already in the pipe begins to flow. Well, same kind of thing happens with electrons. As soon as we close the switch on our system, our circuit, it allows those electrons that are already there to just get pushed along by the voltage in the battery. And so neither the water nor the electrons concentrate in certain places. It just flows continuously in a loop. Loops are sometimes called circuits. That's why we call these electric circuits. But when the switch gets turned on, the mobile conduction electrons in the wire and the filament begin to drift through the circuit, and this allows the light to shine out of the bulb. And so this is essentially what a bulb looks like. There's a wire that comes in one side, wire that goes out the other side. I'm not sure which one's the positive and which one's the negative. It's kind of irrelevant. But basically, when the electrons come in, they pass through our filament. The filament gets hot as a result of the resistance in it and begins to glow. And that's what gives the light off. Then it passes back out the other side and continues back to the battery and then comes back, and so on and so forth. So what happens to the mobile conduction electrons when you turn on a flashlight? They begin to move, current flows, and our device begins to operate, whether it's a bulb or a toy car or whatever it happens to be. Now, electric circuits. For an electric circuit to work, there must be a continuous flow of electrons. There can be no gaps in the wires. Mouse comes along, chews one of the wires. Wire gets bent too many times, finally breaks. This causes a problem. A bulb, eventually the filament will sometimes break. If it breaks, the system is not going to work. So any path along which electrons can flow is a circuit. A gap is usually provided by an electric switch that can be opened or closed to either cut off if we open it or allow the electrons to flow if it's closed. Now, the water analogy is good, again, up to a certain point. Again, break in a water pipe usually results in a leak. But if we have a break in an electric circuit, it completely doesn't work. It just stops. Opening a switch stops the flow of electricity. If we open a water faucet, the water flows. So that's backwards. If we close an electric circuit switch, then the electricity does flow. If we close a water faucet, it stops the water flowing. So little minor differences there, but nothing too major to worry about. So most circuits have more than one device that receives electrical energy from a battery, generator, whatever it happens to be. And these devices are commonly connected in a circuit in one of two ways. We connect it in series or we connect it in parallel. In series, basically, devices in the circuit form one single pathway. It's kind of like a racetrack that you can only go one way. If there's a crash on the racetrack, the race has to stop. It doesn't work anymore. But when we connect in parallel, it's, the devices have branches off of the main circuit. And so each of these branches has its own flow from the battery. And so you can miss the problemed area. The problemed area doesn't work, but the other areas do still. Might liken this to a demolition derby. Okay, you don't have to go around one path. There's many paths you can travel. Some of them might be clogged up by a crash. Other ones you can go around and make it there. So how can a circuit achieve a continuous flow of electrons? It must be a complete circuit. It has to, again, flow all the way around, unimpeded, unbroken. And if it is broken, it will not work. So series circuits and parallel circuits are what we're going to look at here to finish up this first part of 35 notes. But basically, if one device fails in a series circuit, then current in the whole circuit stops. Nothing's going to work on that particular circuit. And so one analogy I have here is when I was a kid, we used to have these Christmas lights. And I'm the oldest of 4 children, so I always got to check out the Christmas lights to see if they worked. If they didn't, because they were series strands, basically you took a new bulb and you went through each one of the old bulbs until the whole string lit up. Okay, that worked nicely if only one bulb was broken. If 2 bulbs were broken, it was over. And basically you had to go buy a new one because you didn't know which were bad. But if 3 lamps are connected in series with a battery, they're going to form this series circuit. Charge flows through each one of the devices in turn, each one of the lamps in turn. And when the switch is closed, current exists almost immediately in all 3 lamps. We don't see the first one light up, then the second one light up, then the third one light up. Basically, as soon as that voltage is applied, it starts pushing those electrons. And when those electrons start pushing around inside of the wires, essentially the lights all light up. So current doesn't pile up in any lamp, but flows through each lamp, and electrons in all parts of the circuit begin to move at once. Now, eventually, electrons move through the bulbs, lighting them up once they've completed the whole circuit. But if there is a break anywhere in the path, you have an open circuit and the flow of these electrons is going to stop. When it stops, all of them are going to stop. Burning out one of the lamps burns out the whole system. The bulbs might not be burned out and inoperable for future use, but they will definitely not work as long as that one bulb is bad. And so here we have a 9-volt battery with a switch, 3 bulbs, and with that switch open, we do not have any of the bulbs lit up. Now, assuming we close this switch, basically what would happen is electrons would begin to flow. And if all the connection at the lights are good, if all the bulbs are good, we should have all of the lights light up. Again, this is a 9-volt battery here. I hope all of you recognize that. But with that 9-volt battery, essentially each one of these bulbs being the same gets 3 volts. Now, for series connections, there's some sort of important characteristics that we see. Again, electric current has just one single pathway through the circuit. And so total resistance to the current is going to be the sum of all the individual resistances along the circuit path. So if each bulb had 2 ohms of resistance, 2 plus 2 plus 2 would be 6. If one was 1, one was 2, and one was 3, 1 plus 2 plus 3 would be 6. So we just add them all up. The current is going to be equal to the voltage supplied divided by the total resistance. So assuming our total resistance was still 6, 9 volts divided by 6 ohms would give us a current of 1.5 amps. Voltage drop or potential difference across each device depends on its resistance. So the voltage drop would be different for each bulb if it was 1 and 2 and 3. But if it was 2, 2, and 2, then the voltage drop across each one would be the same. And the sum of all the voltage drops is always going to be whatever the voltage of the source is. So 9 volts would be the ultimate sum of all of the voltage drops. Again, the main disadvantage of a series circuit, one device fails, current in the whole circuit stops. Some cheap light strings, again, are connected in series. When one lamp burns out, you have to replace it or it's not going to work. So what happens to the light intensity of each lamp in a series circuit when more lamps get added to the circuit? I add more. What's going to happen is I'm going to see that there is a dimmer and dimmer and dimmer bulb each time I add another bulb. So if I have a series circuit, current through one of the bulbs is 1 amp. Can you tell what the current through each of the other 2 bulbs is going to be? The answer here is yes. If it's 1 amp through the first one, it's got to be 1 amp through the second one, it's got to be 1 amp through the third one, and so on and so on and so on. Now, the second question is a little more difficult to go through and answer because they left off some information, but we're going to assume it's a 9-volt battery that we were just talking about. If the voltage across bulb 1 is 2 volts, voltage across bulb 2 is 4 volts, what's the voltage across bulb 3? Well, 2 plus 4 is 6, 9 volts total, so bulb 3 has to be 3 volts. So what happens to current in other lamps if one lamp in a series circuit burns out? They go kaput. They're done if the other bulb has burnt out. All right, and then parallel circuits. In parallel circuits, each device operates independent of the other device because they have a separate path. A break in one path doesn't disrupt the flow of charge in the other paths. So again, it's like kind of a crazy race where you have multiple paths you can do to make a lap. But if one burns out, the other ones still have to go. So in a parallel circuit that has 3 lamps, each electric device has its own path from one terminal of the battery to the other. Okay, there's a separate path for each device. And so in contrast to a series circuit, parallel circuit is completed whether all 2 or only 1 lamp is lit up. A break in any one of the paths is not going to disrupt the flow of charge in the other path. So if we look at this one, again, this is a parallel path. If this is the negative and this is the positive, then basically what we have here is it would flow out the negative and it would go through here. It's complete. We've got a whole loop. So this one lights up. We leave here the negative. We go this way. It goes through here. It goes through the switch, comes back, hits the positive. We've got a whole loop. So that one's working. This one here, we go through and we hit a roadblock here. We hit that roadblock and we're not going to complete our circuit. And without completing our circuit, our bulb cannot light up. So one bad one does not ruin the other two. And so if you look at some of the older cars, like I'm talking like 40s, things like that, a lot of times what happened is they had series circuits in them. So if your tail light went out, your dash light went out too. Well, this causes some problems. So they got smart and they said, well, let's start, making these parallel setups. So tail light goes out and your dash lights still work. So the major characteristics of a parallel connection, each device is going to connect to the same 2 points A and B so that you have a connection to the positive and a connection to the negative side of the battery. And so because you connect to this same A and B point, the voltage is the same across each device. Well, the problem with the voltage being the same across each device is this last one down here. As the number of parallel branches increases, you're going to draw more juice out of the battery quicker. And so, you're okay. It's just your battery is going to burn out a little sooner. The total current divides among the parallel branches. The amount of current in each branch is inversely proportional to the resistance of the branch. Again, more resistance, less current. And the total current is the sum of the currents in its branches. So from the battery's perspective, the overall resistance of the circuit is decreased. This allows for more current to flow. When more current flows, again, your juice from your battery is drained quicker. So overall resistance of the circuit is actually less than the resistance in any one branch. So let's say we had a 3, a 2, and a 1. Well, what we are going to see in our calculation section that we're going to do some notes on next week is that you're going to see the total resistance be less than 1 in a parallel circuit. If we look at a series circuit, we had a 3, a 2, and a 1. You add those up. So 3 plus 2 plus 1 is 6. It's always greater than the biggest individual resistance in a series circuit. And so what happens to the light intensity of each lamp in a parallel circuit when more lamps are added into that parallel circuit? Lamp intensity stays the same because each branch is going to get the same voltage passing through it. So what happens if one device in a parallel circuit fails? As long as the others are operational, they're still going to work. So that's the first half of 35 notes.